-1, -2, 1 and 2. So -1 and -1 and +1. Okay. So at the 0 is 0. Let me use a different color, maybe this green right here. Then -1, -1. Then a negative the square root of 2, which is -1.41 somewhere here. And I don't have to look at the other side. I'm done. Because whatever I have here, I have to have here. It's mandatory. Oh, I forgot to write that this is an inflection point. Second derivative changes sign, and it's 0 here. Okay, so again, 1, 1. And the square root of 2, 0. Okay. So the function is decreasing, opening up to a local minimum. Decreasing, opening up to a local minimum. Increasing to the inflection point, still opening up, where it changes concavity, because it hit the inflection point, changes concavity all the way. Now it's going to be opening down. It's increasing to a local maximum of 1, 1. And then decreasing towards the other x-intercept, the square root of 2, comma 0. So this was the function f of x, x the square root of 2 minus x squared. Any questions? Any questions? Okay. Would you like to do anything else from graphing? Would you like to choose other graphs? We can come back to look at other graphs later if that's what you want. You tell me what you want to do, or we will continue. I like to talk about optimization. Anyone? Any suggestions?
I just want to double check.
Yes?
If we were given like a picture of a graph like this,
Yes?
kind of knowing what, like, you should be able to get relatively close the creation of that table just from looking at the graph if you know all the rules, right?
Theoretically, yes. And if you can determine these numbers.
Well, I mean, if the graph was already given and a question was like, find all these elements of the first derivative and the second derivative.
In other words, where is the function increasing or decreasing? Where is the function?
Yeah.
Yes, where it's concave up, concave down, where it has a local max, local min, absolute max, absolute min. Yes. Inflection point. Yes. Yes.
Thank you.
They work in sync, right? So what I saw here and summarized, increasing, decreasing, local max, inflection point, and so on and so forth, concavity, I transferred in here, including the symmetry. Once knowing that it's the function is odd and I graph this, I don't need a table. I can come up with this part just simply looking at this and knowing that the function is symmetric with respect to the origin. Good. Anything else? Okay, so I will continue with optimization and then Newton's method, and then we will have at least one session, 2 sessions, whatever you need to review all this. So for that 7 is optimization. Optimization deals with max-min for real-life situations. This is a big branch of mathematics. Big branch. It's like as big as algebra, as big as geometry, as big as trigonometry. Big topic. So I can open the book and we can choose from the book, or I can choose the first. Let me share. I think I opened up the book already. Here it is. So we can both decide.
What is optimization again?
Optimizing something, finding the optimum, finding max, min. Finding the maximum of a function, maximum profit, maximum area, minimum cost, minimum distance. It's a very big topic. I like to start with let me choose the first one and you will choose the next.
Does the concept of the optimization have anything to do with like what we're looking at last chapter with like marginal costs and stuff?
Furthermore, when we look at the marginal cost was the derivative of something, right? So we wanted to determine the rate of change. But the optimization is more than that. We want to find the maximum of a function and the minimum of a function. We want to advise. So let me just give you an example, and I'm sure you're going to feel a little bit better after the first example. I don't want the farmer yet. We can. This is from algebra. The farmer, but we can choose that, of course. But I would like to start with something like this. A box with a square base and open top. So problem 18. Let me copy it and then I'll stop sharing. A box with a square base. So I'm going to draw a box. You'll see it in a moment. Okay, square base. An open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. So it has an open top, and we want to minimize the amount of material used, which is minimize the area. That's what the material used means, right? To create this box. So I have a box with a square base. I'm going to indicate that by saying the length and width have the same measure, and I'm going to call that h. And this is so much better. I don't need my heavy book. Much better. Okay, so we are given the volume of the box, so we need to determine a box of this kind with a square base and no top. It says open top, so we don't need to calculate or include the area of the lid. There is no lid, and but we want to minimize the material that we are using, which means that I'm going to call it the area. So the area is minimum. But how can I find a minimum area? Only if I find the function, and only if I find its derivative, and only if I find its critical numbers, and only if I determine that it changes sign, blah, blah, blah. So I have to create a function that I will minimize, as we just did so far in this chapter. So the area of this box is definitely the base, which is x squared, plus 4 identical sides. So the front is x times h. All the other sides are base times height, so there are 4. So I'm having difficulties here only because I have 2 variables. One of them has to go away. But I am given a piece of information that I haven't used yet. I am told that this box has to have a volume of 32,000 cubic centimeters. Okay, I know that the volume of such a box is area of the base times the height, and I know that this has to equal 32,000. Clear? H equals, anyone? I'm going to sip some water till you tell me what is h equal to.
32,000 divided by x squared?
Absolutely. So then I have, which will replace h here. Knowing that, now I can say, guaranteed I have a function of x. I couldn't say that here because I had two variables. So this is x squared plus 4x multiplied by 32,000 over x squared. This is my function. Yes, it's not cleaned up yet. I will clean it up by simplifying an x and multiplying 4 by that number. But this is it. From this moment on, everything is a piece of cake. I will differentiate, I will set it equal to 0, find critical numbers, and find the maximum, minimum, whatever I need. Is this better, Mark? Is the idea clearer?
Optimization?
Yes.
I think it's getting there.
Yeah, that's exactly what we're trying to do. We're trying to...
I have a question real quick.
Yes.
Where did the 4xh come from a equals x squared plus 4x?
Okay, so very good. So the surface area of this box, let me see. I have a box here. Here it is. Here's my box. So it has one side, base times height, plus base times height, plus base times height, plus base times height. So this surface, the back, and the side. And they're four identical. Why they're identical is because the base is a square. So the area in front is x times h. The area on the side is x times h. So they're 4.
Okay.
Better?
Yes.
Okay, perfect. So then, in the next step, which page I'm on? Is it 5? Yes, it is 5. Okay, so I have x squared. I will simplify an x. X in the denominator, 3 zeros, 8 and 12. Okay, so a prime of x. Can anyone tell us? Anyone who hasn't said anything yet? Josh, Carson, anyone?
2x plus
Careful.
1
Careful. Careful.
plus 0.
Careful. Careful. Let's write it on the side again. This is very important. 1 over x prime. I need this for the next chapter. Please, I'm begging you to remember this. Please. Please. So 1 over x prime equals negative 1 over x squared. Is that okay, everyone?